What is Treewidth by David Eppstein? I'm Dr. Samuel Alan Alexander, mathematician and philosopher, still here, and I'm reading the article What is Treewidth by David Eppstein, published in 2025 in the notices of the AMS. The tree width of a graph, a positive integer defined using a tree of sets of vertices, is central to graph structure theory and the parameterized complexity of algorithms. Its many areas of application include sparse numerical linear algebra, Bayesian inference, control theory, game theory, low-dimensional typology, network science, and algebraic geometry. A common definition of tree width involves tree decompositions, of which the following is a special case. A graph is outer planar if it can be drawn with its vertices on the boundary of a disk and its edges as non-crossing curves in the disk. Adding artificial edges, we can augment this drawing to a triangulation, a subdivision of the disk into triangles with the following properties. Property 1. The edge-to-edge adjacencies of the triangles form a tree. Property 2. Each graph vertex belongs to triangles forming a connected subtree. Property 3. Each graph edge belongs to at least one triangle. A tree decomposition then consists of a tree like the tree of triangles whose nodes are associated with sets of graph vertices called bags. In the outer planar case, each bag contains the three corners of a triangle. More generally, tree decompositions may have larger bags but must satisfy properties 2 and 3. Each graph vertex belongs to bags forming a connected subtree, and each graph edge has both endpoints in at least one bag. The width of a tree decomposition is the size of the largest bag minus 1. The tree width of any finite undirected graph is the smallest width of any of its tree decompositions. The minus 1 adjustment ensures that trees have width 1. Root any tree arbitrarily, then use bags containing each vertex and its parent. The tree of triangles of an outer planar graph has width 2. Tree width has many equivalent definitions. It is the maximum clique size minus 1 in a chordal supergraph minimizing this size. It is the maximum number k of cops that a robber can escape in a certain pursuit evasion game. The maximum k such that some function called a haven maps positions of less than or equal to k cops to an unoccupied subgraph into which the robber can escape, and the maximum k for which in some family of connected subgraphs, all touching each other, called a bramble, less than or equal to k cops always leave an unoccupied subgraph into which the robber can escape. Tree decompositions and chordal supergraphs are in some sense dual to havens and brambles. A structure of the former type provides an upper bound on tree width, whereas a haven or bramble provides a lower bound. Tree width is the top element in a certain lattice of well-behaved functions from graphs to numbers. Many other graph parameters are both upper bounded and lower bounded by a function of tree width. There's a figure. Figure 1, an outer planar graph in black, and a tree of triangles forming a tree decomposition in gray. Structure. Tree decompositions, with bag size replaced by other measures, play a central role in the work of Neil Robertson and Paul Seymour on families of graphs closed under minors, the results of edge contractions and vertex or edge deletions. I took a combinatorics class with Neil Robertson. Interesting guy. Brilliant mathematician. Anyway, in 23 papers published from 1983 to 2012, Eppstein continues, Robertson and Seymour found that the graphs in any minor closed class have tree decompositions in which each bag induces a torso, a graph of bounded genus with certain constrained embellishments, and in which adjacent bags share few vertices. This structural result was the key to their proof of Wagner's conjecture, that every minor closed family can be characterized by finitely many forbidden minors, in the same way that the planar graphs are exactly the graphs that do not have K5 or K33 as minors. Edge contraction and deletion cannot increase the tree width of a graph. Tree width is minor monotone. Thus, the graphs of tree width less than or equal to W have finitely many forbidden minors. As Robertson and Seymour also proved, every minor closed family of graphs that has a planar forbidden minor has bounded tree width. The planar graphs themselves have unbounded tree width. An n by n grid graph has tree width n, and every graph of sufficiently high tree width contains an n by n grid minor. It was in the context of this work on planar forbidden minors that Robinson and Seymour gave the name Treewidth, or as they wrote it, tree-width, to the concept we now study, although it appeared earlier under other names. More recent work has shown that the graphs in any minor closed family, and in some families that go beyond graph minors, have a different structure. Each graph in the family is a subgraph of a strong product of graphs, H strong product P, where H has bounded tree width and P is a path. Here, the strong product has as vertex set the Cartesian product of the vertices of the two given graphs. It has an edge between two vertices when, in each factor graph, the corresponding two vertices are adjacent or identical. This product structure in turn has been used to solve many old problems in graph theory on Q layouts of graphs, on non-repetitive and centered colorings of graphs, on implicit label schemes for graphs, and on universal graphs for families of graphs. Computation. The use of Treewidth in graph algorithms can be illustrated by graph coloring, a problem that is NP complete for arbitrary graphs but polynomial time solvable for graphs of bounded Treewidth. Any graph of Treewidth W can be colored with W plus 1 colors, not necessarily optimal, by choosing a root bag in a tree decomposition, processing all bags in order by distance from the root, and assigning each uncolored vertex in each bag a color distinct from its neighbors in the same bag. Any other neighbors of such a vertex can only be in bags that come later in the processing order, so the resulting coloring is proper. With this bound on the chromatic number in hand, an optimal coloring can be found by processing the bags in the opposite order, bottom up from leaves to the root. At each bag, for each C from 2 to W plus 1, store a set of valid C colorings, assignments of C colors to the vertices of the bag that are compatible with a proper coloring of the induced subgraph of all vertices and descendants of the bag. To find the valid C colorings, check for each color assignment whether it's a coloring of the induced subgraph of the bag and is consistent with an already computed valid C coloring of each child bag. The whole graph is C colorable when there exists a valid C coloring at the root bag as determined after processing all bags in this way. Because this algorithm considers all color assignments within a bag, it takes super exponential time in the bag size per bag. However, the number of bags in a tree decomposition can be assumed to be linear in the number of vertices, so for any constant bound on width, this algorithm takes time linear in the graph size. This type of time-bound polynomial of fixed degree, whenever some parameter such as tree width is bounded, is called fixed parameter tractable. Constructing optimal or approximately optimal tree decompositions is also fixed parameter tractable, so we need not assume that the tree decomposition is given as input. Fixed parameter tractable algorithms are the main topic of study in parameterized complexity theory. The same sort of bottom-up processing of a tree decomposition applies to many other problems. A powerful algorithmic meta-theorem known as Courcell's theorem provides a fixed parameter tractable algorithm for testing whether a given graph models any quantified Boolean formula whose variables represent vertices, edges, sets of vertices, or sets of edges. Here, the parameters are the tree width and the length of the formula. For instance, C coloring has a formula involving the existence of C sets of vertices, one for each color class. In a different direction, tree width-based algorithms can often be extended beyond graphs of bounded tree width. For instance, in planar graphs, one can find a bounded number of bounded tree width subgraphs that cover the whole graph with little overlap, or that cover most of the graph disjointly, and then use these systems of subgraphs for fast and accurate optimization algorithms for many hard graph problems. Another approach uses Robertson and Seymour's grid minor theorem. If a graph has a large grid minor, one can use this somehow, perhaps either solving the problem directly or removing an irrelevant vertex from the middle of the grid, and if it does not, then one can apply algorithms that assume bounded tree width. This combination of grids and tree width in algorithm design has been formalized in the theory of bidimensionality. Both Courcell's theorem and bidimensionality won their authors the Nerode Prize, an annual award for outstanding research in parameterized complexity in 2022 and 2015 respectively. An area of active research is the extension of tree width to other related width parameters that can be bounded on dense graphs, apply to directed graphs, or characterize the graphs on which efficient testing of logically defined properties is possible, as well as longer studied variants such as bandwidth, branch width, carving width, clique width, cut width, and path width. Newer alternatives include twin width, which characterizes the ordered graphs equipped with a total order on vertices, for which first-order model checking is efficient, and flip width, defined through a pursuit evasion game like the cops and robbers game for tree width, and conjecture to characterize the unordered graphs on which first-order model checking is efficient. Applications. Graphs are a frequent abstraction in many other problem domains, and the strong relation between treewidth and algorithmic complexity is reflected in these domains. For instance, in sparse numerical linear algebra, the method of generalized nested dissection allows for the fast solution of systems of linear equations defined on graphs of low or sublinear treewidth. The treewidth of a given belief network controls the complexity of junction tree algorithms for machine learning and Bayesian inference, and of algorithms for inferring the belief network when it is not given. Similar methods can also be applied to stochastic optimal control problems. In game theory, finding equilibria in certain coalition-forming games is intractable in general, but becomes efficient when a graph underlying the game has bounded treewidth. Extensions of Courcell's theorem to triangulated manifolds with low treewidth dual graphs have been used to compute invariance in low-dimensional topology involving taut angle structures, discrete Morse theory, and Turayev-Viro invariance. In network science, low treewidth allows many types of queries on network databases to be answered more efficiently than otherwise. Although large real-world networks modeling roads and infrastructure, social interactions, biological subunits, and interrelated pieces of knowledge tend to have high treewidth, these networks can often be decomposed into smaller, low treewidth subnetworks to which these fast query techniques apply. The structural aspects of treewidth can also be reflected in other areas of mathematics that are less directly computational. As one example, in algebraic geometry and tropical geometry, the treewidth of certain graphs can be used as a lower bound for the gonality of these graphs, and hence for the gonality of Riemann surfaces and tropical curves associated to these graphs. Is this a graph theory paper or a zoology paper? I'm Dr. Samuel Allen Alexander, mathematician and philosopher. Please like, comment, and subscribe. I'll see you in the next video.